Hi, and welcome to the course. This is the course introduction, and I'll tell you why you're going to love this course. So what exactly is this course about? Well, it's about computer vision, CV, and deep learning, DL. And these are a bunch of terms you will be learning throughout this course, because deep learning is revolutionizing the world as we speak. It's enabling machine to learn such complicated tasks that were thought impossible a mere 5 years ago. And the reason this is happening is because with the combination of increasing computer speed, the wealth of research that's being done all over the world by tons of universities, and just the rapid adoption and growth of the technology industry, it's causing deep learning to experience a massive growth worldwide, and it's going to be one of the biggest industries in the near future, I guarantee it. The 21st century is the birth of the AI revolution, and data has already become the new oil. The computer vision industry alone right now is worth 12 billion and is projected to be worth 17 billion US by 2023. And at this point in time, deep learning computer vision scientists are paid up to 1,000 US a day as demand continuously outstrips supply. But what exactly is deep learning? And what about computer vision? And what's a computer? Just kidding. Now, deep learning is a machine learning technique that enables machines to learn complicated patterns or representations in data. And in the past, why deep learning is so good right now is because previously, machine learning scientists would have to be tweaking and doing a bunch of complicated statistical analysis and picking out data features just to get their models to work right. And then their models typically worked poor when the data got complicated. So what's deep learning? So let's pretend we have an untrained brain, this guy. And he's capable of learning, but right now he's just a blank slate. He has no prior knowledge. So imagine now we show this brain thousands of pictures of cats and then thousands of pictures of dogs. This process of teaching and training the brain is basically how he learns. And now he can see a picture of a cat that he's never seen before, and he'll know it's a cat. So that's essentially what deep learning is. So computer vision. Computer vision is one of the most important parts of the AI dream. Remember the scene in Terminator 2 when Arnold Schwarzenegger was looking at the bicycles and all the stuff and he figured out he knew exactly what everything was? That is what actually motivated me to want to learn computer vision. And this was like when I was a child. So machines that can understand what they see will change the world, and I'll tell you why. We take for granted how amazing our brain is at vision processing. Our brain, it has 6 layers of complicated vision processing tools. In fact, the majority of our brain is actually devoted to visual processing. And this is a high-level diagram of actually what happens. It's so complicated. Because take a look at this example. This is a state-of-the-art computer vision object detection algorithm. And it's looking at some buffaloes, actually, not cows, but it thinks it's a cow, walking through, it's a wildlife park, it looks like. Now, all that our computer vision algorithm can pick up is that there are 4 cows, when in fact there are 1, 2, 3, 4, 5, 6, 7. And it's not picking up that there is a dusty environment, it's in leaves, there's grassland, dry grassland. We can infer so much more from this picture alone than our state-of-the-art computer vision algorithms can. So while this is an amazing achievement on its own, we still have a long way to go. Robots or machines that can see will be capable of so much. You can have self-driving cars, robotic surgeons, and advanced medical diagnostics. Robots that can navigate our world and become farmers, chefs, and assistants. You can have intelligent surveillance that can pick people out and figure out exactly when crimes are being done. You can create art with your deep learning neural networks now. And we can have improved video searching and image searching, and even have some fun social applications. And deep learning can actually improve photography, cleaning up these images and processing it into this. So who should take this course? If you want to be in the forefront of the job market for the AI revolution, then this course is for you. Or do you have an amazing startup idea involving computer vision, but you're not sure how to execute it? Or are you a university or research student who needs help in building your fancy deep learning CV models? Or even if you're an enthusiastic hobbyist who just wants to build some fun computer vision applications, then this course is for you. So what exactly is this course about? Well, we're going to apply deep learning techniques to computer vision tasks such as image classification, image segmentation for medical applications especially, object detection, neural style transfers, and generative networks where we age a face from this age to 60 plus. So, my name is Rajiv Ratan. This is me here. And I'll tell you a bit about myself. Besides having a noisy mouse, I was a radio frequency engineer in Trinidad and Tobago for 8 years, where I worked on a number of projects and was manager of the section before I left. And I left to basically go do my master's in artificial intelligence in the University of Edinburgh, which was a wonderful experience. And I specialized in robotics and machine learning. And that's how I got exposed to computer vision. After that, I actually got into a startup incubator, Entrepreneur First, in London. I was part of the EF6 batch. And after I completed that, I actually landed a number of jobs. I was the CTO at an edtech startup called Dozenal. Then I became the VP of engineering at Keepler. And then I left to become the head of computer vision at Blinkpool, where I currently am. And I also created a very popular Udemy course called Mastering OpenCV in Python. So this is a quick preview of my existing Udemy course. Basically, it's a very informative course on how to use OpenCV in Python. And fortunately, I'm throwing in half of this course as a free bonus. Basically, you'll be able to strengthen your knowledge in computer vision by understanding OpenCV. However, it is completely optional. You don't need to do this segment to understand deep learning. So what will you be able to do after you take this course? You'll be able to create and train your own classifiers using a variety of CNNs like ResNet, VGG, Inception, and basically create your own custom CNNs. You can use techniques like transfer learning and fine-tuning. You can analyze and improve your performance by understanding all these graphs and what they actually mean. And then I move on to teaching you a lot of advanced concepts that help you improve your model performance. And we do all of this using Python and Keras. Next, I actually teach you a lot of image segmentation and understanding how to use CNNs to do image segmentation, which has a lot of useful applications in medical imaging. Next, we do object detection, and we actually make our own object detector in this course. And then we go on to neural style transfers and deep dreaming, which allow us to make some awesome looking art like this. And then finally, we go on to generative adversarial networks, where I go through a bunch of projects with you and make sure you understand this very well. So I made this course because computer vision is continuously evolving, and in this fast-moving field, it is extremely hard for a beginner to even know where to begin. I use Python and Keras with TensorFlow's backend, and these are by far the most popular libraries used for deep learning computer vision today. And while there are many good tutorials out there, so many of them have outdated code or just provide broken setup and installation instructions. And there are too many tutorials that just get way too technical and theoretical too fast, or on the opposite end, they're just way too simplistic and teach you things without making you understand the key concepts. The requirements for this course. Well, you need little to no programming knowledge. However, obviously some familiarity with Python is very useful. However, it's not a prerequisite for this course. You do need to have some high school level math, and obviously college level math will definitely help you expand your knowledge into deep learning. However, it's definitely not necessary to execute anything in this course. You also need a moderately fast laptop. You don't need a GPU, luckily, and that's a very big plus in this course. However, you do need at least 20 gigs of hard drive space for your virtual machine and datasets. So what are you getting in this course? You're getting 600 plus slides of excellent teaching content. You're getting 15 hours of video, including an optional 3-hour OpenCV tutorial. You're getting a comprehensive deep learning computer vision learning path. And I've spent a lot of time developing this path, these topics that will bring you up to speed and almost a master in deep learning computer vision. You get exposure to the latest techniques as of late 2018, and you get a free VirtualBox development machine. That is something you can't put a price on because installing and setting up everything takes hours. This will save you so much frustration, I guarantee it. And you get 50 plus IPython notebooks to use as tutorial guides for furthering your knowledge. And you get to do 18 plus amazing deep learning projects in this course. So what's the course outline here? First, I start with the introduction to computer vision and deep learning. Then I get you up to speed with our installation and setup guide. Then we start experimenting with some code, just having fun using Keras. And then we learn all about neural nets and convolutional neural nets. This is a very important section in the course. And then we start building progressively harder and harder CNNs. And then we start doing some image segmentation using UNet. We use object detection with TensorFlow Object Detection API, as well as YOLO. Then we move on to deep dreaming and neural style transfers. And then we conclude with generative adversarial networks, and then finally just do an overall computer vision overview. So thank you and welcome to the course. Hi, and welcome to section 2, where I introduce computer vision and deep learning. Now in this section, we first deal with what actually makes computer vision hard, and generally explain what is computer vision. I also start talking about what are images, because you have to have a good concept of what images are in order to actually comprehend what we're doing in this course. And lastly, in this section, I talk about briefly a bit about OpenCV, talk about the brand new OpenVINO, and I talk about their limitations because these are not ideal for deep learning, and I'll tell you why. Okay, so welcome to section 2.1, where I tell you a bit about what exactly is computer vision and why is it so hard. So briefly, computer vision is a cutting-edge field of computer science that aims to enable computers to understand what is actually being seen in an image. Now, computer vision is an extremely interesting field and it's undergoing remarkable growth in the last few years, but it's still very hard. And while there have been a number of breakthroughs, we're still far from where we want to be. It's mainly because computers don't actually see like we do. Our brains are incredibly good at understanding what we see. Like, just look at a room around you. I'm pretty sure you're seeing your desk, you're seeing number of items on your desk, you're seeing like walls, windows, I hope, all those things. I mean, we have object detection algorithms that can do all of this, but still they're a far cry from what we can do instantly. And this is exactly how a computer sees an image. What you're looking at right now is a big array. I'll explain what this is later on in the course. But as you can see, computers don't see at all like we do. They just see a bunch of numbers. And there are many other reasons why it's so hard for computers to understand what they're seeing. Firstly, you remember computers see through a camera lens. And lenses have limitations. Lenses have resolution issues. You know about megapixels, like your phone megapixel race. Your phone's currently at like 12 to 20 megapixels for good phones. And also sensors. Sensors are very sensitive to noise. Our eyes can see pretty damn good in darkness. Well, almost darkness, in dark light at least. However, camera sensors have a very tough time of actually dealing with that. And that's why you get what is called noise in these images. And noise basically creates artifacts, as you can see these little artifacts right here, that essentially hide detail in images. And this is an example of a poor resolution camera. This only happens if you zoom up to something here, okay? Normally our camera sensors are pretty good at capturing major detail right now. Also, they have viewpoint variations. We know this is a Statue of Liberty, even though it's at different angles in this picture. But it's actually going to be pretty difficult for a computer to figure out each time it sees a statue, is this a Statue of Liberty or is it a new statue I'm looking at? Now, most likely he can figure it out now. However, it is still a challenge. And even this one is just slightly rotated, but it looks a bit different. There's also changing lighting conditions. Objects can look incredibly different. Look at this one. These look like silhouettes and they're brightly lit over here, just from having a simple lighting change. And then there are issues of scale. I think this gives you a good idea of what I mean. Also, this is Taj Mahal from pretty close up, and this is it from far away. It definitely looks like two different buildings. However, we can actually tell it's the same building. Then there's also non-rigid deformations. These are the same animals essentially here, but they're in different poses. Remember, a dog can be curled up looking like this, or he can be on the guard looking like this. So it does look drastically different. And then there's occlusion, where it's basically partially hidden or partially obstructed objects. And then there are issues of clutter. This is an octopus. It's actually a bit hard to see. It's camouflaged by his changing skin tone here. And this is a city, and I assume it's China somewhere, and it is very cluttered. All these signs and stuff. And then there's also object class variation. These are all beds, but beds can take many shapes, sizes, colors, styles. So we know this is one general category, a bed. However, it's, again, think about it from a computer's perspective. Is this a bed? Is this a bed? They look very different. This is clearly a sofa, but it's probably a sofa bed. So you know it's going to be tough for something like a computer to figure out without seeing maybe millions of examples of an object. And then there's optical illusions. This is not a hole in the pavement. This is actually a drawing, and so is this too. And this can actually either be a vase or a vase, depending on how you want to say it, or two faces facing each other. And yet, despite all those challenges I just discussed, there have been many successes in computer vision. We have very good and very accurate license plate readers technology, and that's been out for quite a while. We have basically very good OCR and even handwritten digit recognition. In many sports, like in cricket, there's Hawkeye, and then it's like in tennis, there's all these like ball projection stuff, ball tracking stuff. In football now, it's quite good. And now, especially with self-driving cars around, we have very good object detection algorithms that can tell what's a pedestrian, what's a stop sign, what's a road, what's a lane. And for those of you who play a lot of video games, Kinect is actually basically a computer vision based device that looks at you and knows how your body is posing. And of course, there's like Snapchat filters and all that fun stuff on mobile phones. All of those things involve computer vision and have been quite successful. Okay, so that's it for this chapter. We're now going to move on to what exactly is an image. Okay, welcome back to section 2.2, where I talk about what exactly are images. Okay, so what exactly are images? Now, the most basic definition I can give you of an image, it's a two-dimensional, remember flat, representation of the visible light spectrum. Now that sounds like a physics definition, but it's actually, in reality, what it is. Remember, light consists of visible color spectrum, which is this zone right here in the electromagnetic spectrum. And we basically call an image basically anything that basically reflects that light, be it on a piece of paper, which is also an image, a painting, something on a wall, all of those things. Could be something on your computer screen, which is exactly what this course deals with here. Those things are images. And effectively, we'll get into this a bit further, but how computers store images is basically in a grid of pixels, and each pixel has a color, which is how we're able to show this on your laptop screen or mobile screen, whatever you're using right now. So how exactly are images formed? Now this goes back to your high school physics work, which you hopefully do remember. But imagine light has been reflected off a tree onto a flat surface here. This is called a film or sensor, if you want to think about it in terms of cameras, or retina in terms of our eyes. And basically, since there's coming at all angles, the image is actually going to be blurred at this point. How do you make it not blurred? Well, you use this. Use a barrier where there's light can only come through this small hole, and this is basically the concept of a pinhole camera. And what happens is that light comes in from all angles here through this hole, projected onto this film, and once this film is at a certain distance, the picture will appear very sharp. And this opening here, this little translucent opening, is called the aperture. Those of you who are familiar with photography will have a very good idea of what aperture means. F-stop. Lower the f-stop, the more light it allows to come in, which is what we want. So image formation. Now, going back to photography again, a lens can now take light from all different angles and focus it at a point on a film to get it in focus. And that's by controlling the lens width here. That's actually how we adjust the focus at this point. So how are images seen digitally? Now, computers store images in a variety of formats. However, they all involve mixing basically colors or hues or brightness or saturation. And the most commonly used one in computer vision is BGR. BGR stands for blue, green, and red. What this means is that in this pixel location right here, location 00, that in your computer screen would be this top left corner. Imagine we have a mix of 3 colors. If you actually take a magnifying glass, I'm pretty sure most likely you can actually see the pixels red, green, and blue at the corner here. And basically to represent a color, basically colors are just mixes of different intensities of these lights. So yellow, like in this shade here, will actually be red at 255, green at 255, and 255 in this 16-bit range is actually the max color. So basically, if all were the max value, you would have white. Green would just simply be red at 0, blue at 0. Brown would probably be a mix of a few of these. I'm not entirely sure what it would be. But that's how we bring color to our screens. And that's how computers store images. Remember this picture I showed you before? Now imagine this is, I believe this was like maybe 20 by 100 or something. I can't remember what I made. But imagine this pixel here is 0, 0. This is also 0, 0, and this is 0, 0 for each color. And the 4 represents the intensity of the blue. The green represents the intensity of the green, obviously. And this number represents the intensity of the red here, 106. So now imagine if all of these were to come together. So imagine all of these coming together and overlapping each other. That is how we represent colors on an image. So this is a flat surface now, and we have an image basically being formed out of this. Now let's talk a bit about arrays, because basically understanding what arrays are will help you visualize, especially when you start doing deep learning, how basically images are stored, what you're looking at. It's actually very, very useful. So if you're unfamiliar with this, pay attention. So imagine a one-dimensional array would simply be one cell of information. Let's bring it up. So it's one line, and each number corresponds to its position on this array. So imagine we have an array. Let's say it stores my grades. And my grades are basically, let's say 0 was math, 1 was English, 2 was physics, blah, blah, blah. So now, if I just said I want my grades, position 1, it brings up my math grade here. That's what arrays are used for. What about two-dimensional arrays? How would that look? Two-dimensional arrays basically have an X and a Y type feel or look to it here. So now we're able to store more information. So now position 0 on this, let's say this is Y dimension, now has 3 rows here, 0, 1, 2. Now this is basically a cell grid. If you use Excel, you should be pretty familiar with this. Now there can be two-dimensional arrays for images, all right? Now I'll talk about that very soon. But typically, images are stored in three-dimensional array, and that looks like this. You have X, Y, and now you have Z. And remember before, I told you we had 3 colors, red, green, and blue, or BGR, to represent the colors of the blue, green, and red, obviously. So now, these are positions here, 0, 0 on the X, Y, but now that has 3 attributes associated with it. And this is basically how it looks. It's like a big block, a 3-dimensional block, where you have 3 rows or 3 depths going back, and each XY position basically represents the mix of that. That is how images are stored. Now, I did mention you can have images stored in a 2-dimensional array, and that would be grayscale images. Grayscale images are actually pretty cool and are actually used often, not super often, but often enough in computer vision, mainly because processing a grayscale image is technically 3 times faster. I don't think it works linearly like that due to all the different matrix calculations your computer has to do, but it is faster regardless, and it's less information being stored. So instead of having 3 rows or 3 depths or 3 columns, not columns, depths, you can consider it going back, there's just one now, and that one basically has the information storing for this here. Okay, so now that you have a basic understanding of what images are and how computers store images, I'm going to move on to OpenCV. And now OpenCV stands for Open Computer Vision. I'll give you more details in the next chapter, but it is critical and very useful in computer vision to know, at least be familiar with OpenCV. Hi, and welcome back. We're on to section 2.3, where I introduce OpenCV and I talk about OpenVINO, which is brand spanking new. It's part of OpenCV 4, the beta release. And I also talk about their limitations, because even though OpenCV is very, very useful, you don't actually need to know any OpenCV to do deep learning and computer vision. I use it quite a bit still, because I am very familiar with a lot of the algorithms, so I tend to use it when there are other libraries that can be doing the same thing. So what I'm saying is that you don't have to know OpenCV, but it's one of the better image processing libraries out there, and you will always need an image processing library when doing deep learning. At least not all the time, but most times. So let's get into it. Okay, so let's talk about OpenCV. Now, OpenCV was officially launched in 1999. It stands for Open Source Computer Vision, and it was an Intel initiative, which I actually forgot, but I just remembered because I have it in the slide. And what OpenCV is, basically, imagine you have research being done on computer vision worldwide by university professors all over the world. And each of them are coming up with their own algorithms and their own stuff to do image processing stuff. So basically, OpenCV was everyone basically combining their stuff into one library, one easy-to-use library, to make it accessible for everyone else. So you developed a function that does this here, all the way in New Zealand. I want to now use that in my software. So now OpenCV was a library that basically brought everything together. OpenCV's core is written in C++, which means it's lightning fast. In Python, we're simply using a wrapper that basically wraps over and calls C++ code inside of Python. It is quite quick too. However, using it in C++ is always faster because there is always some overhead when doing this kind of stuff in Python. It's not bad. It's actually, I've done some very high performance stuff using Python's OpenCV. So I don't think it's that much of a performance sacrifice. Maybe at least for some things it might be. Let's go back to it. So the first major release was in 2006, officially. Even though it was launched in 1999, I'm guessing it took from 7 years to actually compile and make sure everything was working, well documented and stuff. Second release was in 2009, which is probably OpenCV 2. And the third was in 2015, OpenCV 3. And the fourth, which is in this year, well, this current year, when I'm actually making this course, and pretty soon in a month or two, it's going to be 2019. But that still means that OpenCV 4, which is still in beta, is quite new and actually has quite a lot of cool features. It has over 2,500 optimized algorithms, and that's quite a bit. I've probably used hundreds, now that I think about it, but 2,500 is insane. It's quite a bit. And it is extremely, extremely useful for computer vision applications, as I mentioned quite a few times. It's available in Windows, Linux, macOS, Android, iOS. All of these things have bindings to Python, Java, MATLAB. I think there are a couple other languages, but maybe not officially supported by OpenCV. Now, this is how OpenCV's website looks. Kind of looks a bit dated, but it's still very up to date. It talks about the new release here with OpenVino Toolkit, the alpha release, which actually just came out last month. And talks about different conferences, news and stuff. Check it out. I actually go to the site quite often just to keep up to date. It's opencv.org. And this is the new release. Intel actually distributed this release a few months ago. It's called OpenVino, and what OpenVino is, it's basically a way to use your CPU and Intel's iGPU to actually use the OpenCV framework to do deep learning. Because as you will see in this course, deep learning on a CPU, while very possible, is quite slow. And I think Intel, because they have such a monopoly on the CPU market, no offense to AMD, I love AMD, but they're not nearly as big as Intel. Intel had to push to actually do this for their CPUs. So now their CPUs are a lot faster in training deep learning networks. And I should mention, it's not just for deep learning. A lot of other algorithms in OpenCV have been sped up now. Now, there are some disadvantages of OpenVino. Firstly, while it's quite useful, it is a bit late to market. TensorFlow and other algorithms such as Caffe and Theano, PyTorch, those have been around for 3 to 4 years by now. And they're established, they're well documented, all the bugs and kinks have been worked out. I'm using TensorFlow and Keras. Keras is basically, I'll get into this later on in the course, but Keras is a API that actually calls TensorFlow code. It's quite easy to use, which you'll find out in this course. But what that means though is that OpenVino is very late to market, and it isn't super useful, mainly because a lot of professionals and researchers still will always use GPUs or even TPUs, which are tensor processing units, mainly because those are super powerful and super fast. No one is going to get ImageNet, which consists of millions of images and takes like weeks to train on GPUs. No one is going to train that on a CPU, ever, period. So OpenVINO basically doesn't have that much usefulness in the computer vision deep learning domain. It may have it for basically people like us who don't have access to powerful GPUs or expensive cloud GPUs. So it could be useful for us. We'll stay tuned. We'll monitor it for the next few months. So far, adoption has been quite slow. I've actually struggled to find example code and tutorials of OpenVINO, and it's still in beta. That could be why as well. So that concludes this chapter, chapter 2, which was basically a basic introduction to computer vision, what are images, and a bit about OpenCV. Okay, so now that we're finished with chapter 2, you're now about ready to set up your complete deep learning environment, and I've made it super easy for you. So go on to chapter 3 and let's get going. Alright, so welcome to chapter 3, where we set up our deep learning development machine. So now that you've gone through the intro, you're now ready to get started setting up your machine. So let's get to it. So now the first step in setting up our deep learning virtual machine is you need to download VirtualBox. VirtualBox is a software that allows us to actually start an entirely new operating system, whether it be Linux, Windows, or Mac OS, although it's not fully supported for Mac OS. But you can actually run an entire new operating system within VirtualBox. It's super cool. It's called virtualization, and it is super fast on new CPUs. They don't experience any slowdown really, and it is entirely useful for us to set up our deep learning machine because deep learning software on Windows is not well supported. However, on Linux or Ubuntu, it is a very good environment for running our software. So what you do now is you download either the Windows or OS X versions according to what OS you're using. So I'm assuming it's going to be Windows, so I've already downloaded it here. So now what you do as well is you download from the link in the resources file, download your deep learning CV Ubuntu.ova file. This is your virtual machine that we're going to set up. So now that you have those two files here, we are ready to get started. So now we have to firstly install VirtualBox. Now, I know this file is quite huge, it's 9 gigs, so you probably would have wanted to leave this overnight if you have a relatively slow broadband connection. However, if you have a fast connection, it should take about an hour. Either way, let's install VirtualBox. So you go to Run, Standard Procedure. I'm not going to do the Mac install video because I don't have access to a Mac, but as soon as I do, I'll upload a video for you Mac users. However, it's a standard installation procedure and all the settings are the same generally for Mac and Windows, so this should relate to you as well. So you leave all the defaults here as well, just press Next, Next again. You can, optionally you can do this if you want, it's fine. This is fine, press Yes, Install, and there we go. Okay, so we've finished the installation process, so now you can start your VirtualBox software and I'll show you how to get everything set up. Alright, so here we are on our VirtualBox Manager software. So please ignore these two virtual machines I have up right now. Yours is going to be blank right now, since I assume it's the first time you're going to be using this. So go to File and Import Appliance, and now go to the directory where you downloaded your VirtualBox.ova file. Alright. So go to Open and press Next. Now I have it set to, for my virtual machine, to use 4 CPUs and use 8 gigs of RAM. That is basically, I have a quad core CPU, so I have 8 logical cores, and I have 16 gigs of RAM in my system. So you're going to want to put it to at least half of what your host system can support. So if you have a dual core, you can use 2 here, and if you have 8 gigs of RAM, you can use 4 gigs here. So we can make those adjustments and leave everything else the same. This is fine. And then go to Import. And now this time is basically a lie. It's going to take maybe about 10-20 minutes. So I'm going to pause the video here. And when it's done, we can start our virtual machine and I'll show you how to use it. It's quite easy. and we'll download and set up our code, and that should be it. Okay, so that's it. We have just installed our virtual machine. So now this is the new one here. Because I already have it working here, it came up as _1. Yours is going to be this one. So either way, it's the same machine. So let's just start this one, the fresh one I just installed. It takes about maybe 30 seconds to boot up, at least on my system. This is all normal, by the way. It's a booting screen for Ubuntu. There we go. So we've loaded our OS. So this is pretty cool. So now you're actually running Ubuntu within Windows. And it's because it's using your virtualization features on your CPU, it's going to run pretty quick. You're not going to notice much of a slowdown. So what I want to do is two things I want to show you. First of all, your password for your virtual machine. Whenever you do sudo or any sort of like system settings where you change users and stuff, the password for this user is 11223344. It's going to be in the attached resources of your file, and I'm going to display it on screen as well, so you don't forget it. So let's just see something here. So what I want to show you is that we have this is our machine, this is our file structure here. So this is our home directory right now. We have a bunch of things installed here right now. Basically these things are a lot of your deep learning libraries, and I have some instructions as well. You don't need to use these right now, but what I want to show you is to basically set up your code and train models. Okay, so stay tuned. Okay, so what I'm going to need you to do is open Firefox. That's a web browser on Ubuntu by default. And what to do is when Firefox boots up, I want you to go to your Udemy account on udemy.com, and with the attached resources to this lesson, which is also the deep learning code library. Just wait for it to boot up here. I think my system has a lot of stuff running right now, but either way, let's just go to udemy.com. And there's Black Friday sale going on right now. How nice. So what to do is basically log into your account, however you've done it before, whichever method you use, and download the resources for the course. That's the code and train model zip file. And download it, and it's going to save in your downloads folder right here. This is the same folder, and this is a file I want you to extract. So double click on this file. It's going to take a bit for 10 seconds or so to open. It's a big file, so that's reasonable. And this file here, I want you to extract it to your home directory here. So let's go ahead and do that. Let's just reduce this clutter in the background. And this takes about a minute, actually much less than a minute to extract. And when it's done, you will see all our code that we need for this course is in a convenient location. So let me just quit this. Oh, close. Okay. And it's doing something, but that's fine. What I want to do is go to home, and now you see this directory here, Deep Learning CV, and this is also a shortcut to that same directory. And let's go back to it here. This is the contents of this directory. So let's sort it on list here. This is all the code and train models you're going to need for this course, and it's conveniently extracted now within your virtual machine. So now let's go back to our our terminal. So let's clear this. So what if we wanted to test our code? So what you do, you press source, type source activate CV. That's our deep learning environment for computer vision, and it's instantly done. And now you type IPython notebook, and some magic happens. What this does, it starts a local server that hosts your IPython notebook browser. So now this is where we run all our Python code. and I'm just going to do a brief tutorial on it here. So now just go to Deep Learning CV. Let's just go to chapter 4, getting started, and let's run our live sketching, because this loads much quicker and we don't need to download any files for this. So to run this block of code, IPython notebooks are basically just blocks of code we can run, and all the variables, everything is stored inside of it. So you press Shift Enter or Control Enter. Shift Enter runs it here. This takes about maybe 5 seconds to import or less, and we print the version of OpenCV that we're using. It's 3.4. If you press Alt Enter, you get a new line below. So that's sometimes convenient, sometimes not. Shift Enter just runs it without producing this new cell here. And to delete it, just press Cut. So now let's run our sketch. Now before we do this, we're going to have to go to Devices, here, Webcams, and tick off our integrated webcam. And now let's press Shift Enter to run this block of code. There we go. So this is our browser, our live sketch. This is me chatting here. This is my microphone, the doors in the back. So this is pretty cool, isn't it? So let's close this. And that is it. So we have all our code here. Everything is pre-installed. All our Keras, TensorFlow, a bunch of supporting libraries. dlib is installed. A lot of things are installed actually. It probably takes about an hour or even 3 hours sometimes to install everything. So that's it. You have your full virtual machine running here. Hi, and welcome to chapter 4, where basically the goal of this chapter is to get you up and running quickly using our development machine. So you get to actually test some already trained classifier models and actually play with OpenCV a little bit. So the section is broken down into 3 chapters, or sub-chapters I should say. The first one we play with our handwriting classifier. Second one, we use an image classifier. And the third one, we use OpenCV to basically turn what your webcam sees, which is going to be you, into a live sketch. So stay tuned and let's get started. Okay, so as I said in chapter 4.1, we're going to use an already trained, and you'll understand what training is later on, but you're going to use something that we actually create in this course in the next couple chapters to classify handwritten digits. So it's going to be pretty cool. So let's get started. Okay, so let's bring up our development environment, and that's source activate CV. And now let's bring up our IPython notebook. So let's type IPython notebook. And there we go. Mozilla should launch, and we should have basically our home folder information here. So let's go to Deep Learning, which is where all our projects, or 90% of our projects, are located. And let's go to chapter 4, which is our first chapter. As you can see, all the chapters are here. And let's open this one. And it should bring up this. This is called an IPython notebook. And I've left some simple notes here, some comments here. This one, I'm not going to actually teach much from this course here, from this code here, sorry. I'm just going to actually execute it, and we get to see what it does. So basically, before I begin, let me just briefly discuss the code. These are our imports here. We're importing OpenCV, NumPy, which is our array processing library, and Keras, which I'll teach you about later on. Keras is basically the framework, the deep learning framework we use to basically control and operate TensorFlow, which runs in the background. And that does all our deep learning stuff. So we're loading the MNIST dataset here, and that's how we're importing this from Keras here. Loading our model, and then this is a function we use to basically draw the prediction, what our model makes, over the actual digit. And You know what? Let's just actually run this and see how it works. So it's loading. This asterisk here means it's loading. Ah, there we go. So now we have basically what this does. It brings up a number from a test data set. Test data set is basically images that the the deep learning algorithm has not seen. And basically it tells you that it never saw this digit before in its life, but it tells you it's able to figure out that this is a 4. So now if you press enter, it goes through another image, and it basically does this up to 10 images here. You can go up to 50, 100, 1,000 if you want. Although I don't recommend going up to 1,000. This is a 2. Actually, this is pretty good. It's an 8. Good. 1, 1, 6, 8, 3, 5, 6. Perfect. So it appears this model that I trained here, called MNIST Simple CNN, is actually quite good at reading our numbers, sorry. So can this work on real numbers now? What do I mean by real numbers? Well, let's find out. Let's run this. If I didn't mention it to you before, Enter and Shift on a keyboard together basically executes the code in the cell block. I should have mentioned that in the beginning, but now you know. Okay, so this is numbers that I actually wrote and took a picture with my phone. And basically the code I've done here, it basically uses OpenCV to extract the digits here. And then it pre-processes it to basically make it look as similar as the training data for the MNIST dataset looked. And let's see. So basically what it did, it took out this one. And you previously saw how the MNIST dataset images were basically grayscale and white on black background. So it picked this out, extracted it here. This is a contour we drew over it here. And immediately it classifies this as 1. And it puts a 1 here. So that's pretty good. Let's see if it gets a 3 correct. Bingo. Got the 3 exactly right. Got the 5 exactly right. 4, 0. Perfect. So all of this here is my OpenCV code, and if you want to understand how this code works, I'm not going to explain it to you thoroughly here, but this should be fine. But I'm actually going to tell you that if you do want to learn this, look at my OpenCV tutorial. It'll teach you all of these things, what Gaussian blur, canny edges, contours, how these things work, how to use functions, and you're sorting your contours here, how to actually sort contours and bring them up and extract them, and then feed them to a classifier, which is what we're doing here, the same classifier we used up here. So we're pretty good. You just actually use a handwritten digit classifier that I built, and you're going to build it soon. Actually, perhaps you can build it right now. This is a code where I'm not going to go through in detail, as I said, but this is a code that actually allows you to train that classifier. It is not as complicated as it looks here. If you're unfamiliar with it, I expect you to be a little confused. What the hell is batch size? What are epochs? What is going on here? Blah, blah, blah. But don't worry. All of these things will be made very simple soon. And basically, you'll understand what these lines mean here, what this means here. This is actually our accuracy of our model, 99.07, which is pretty good. Not top of the line state of the art, but pretty good. And stay tuned. You're going to learn how to do this in the upcoming chapters. Okay, so in section 4.2, we're actually going to use probably a little more complicated image classifier, one that classifies 10 different objects, and you'll see those objects very soon. So let's get started. Okay, so now let's open section 4.2, which I called image classifier CIFAR10. Probably could have come up with a cooler name. Okay, so I mentioned we're going to classify 10 different objects. What this model CIFAR10 is, it's a pretty large model dataset that has thousands of pictures of airplanes, automobiles, birds, cats, deers, dogs, frogs, horses, ships, and trucks. Not entirely sure how they chose these categories of images, but maybe it was just for purely research purposes to build image classifiers to detect how well it can pick out these images from data it receives, from images that it receives. So again, this is a model I trained, and I don't believe this model is actually super accurate, but let's run this model and let's find out. There's an error here before, but probably maybe I fixed it. Let's find out. Ah, it didn't happen again. Good. So now, it says this is a ship, and this is clearly a car, so we immediately know this model isn't great. But it got the day right. At least I think this is there. Got the truck right. Truck again. Got the frog right. Looks like a frog, but it was a ship. It's called it. Automobile. Bird. Definitely not a truck. It looks like a cat. This is a truck. So let's run it one more time. Remember to run, you press Shift and Enter together, and it usually pops up on a window here. In Windows, it pops up on top of the screen, which is quite nice. On Ubuntu, it comes up in the background, so you kind of have to look for it there. But it kind of does a little shimmy shake thing here, so if you're paying attention, you should have seen it. So it got the ship right. It's not a truck, it's a frog. It's not a dog, it's a cat. It's not a ship, it's a bird. This is a dog. This is a deer. This is an airplane. This is car or truck. I'm not sure entirely what they would have labeled it as. Truck for sure, truck for sure. So, as I said, this model I trained here isn't a very good model. I think the accuracy I got on this one was 60 or 70%. I actually could have got a lot higher if I left it for longer. Probably didn't want to. But it gives you a good idea of limitations of training a model for a short period of time, which was this, and this was called Safari Simple. I think I used a very simple CNN for this one. And later on in the course, you're actually going to use far more complicated models that we're going to train for a longer time to get even higher accuracies on these. Okay, and now welcome back to chapter 4.3, where we're now going to use OpenCV a bit more. Now, I didn't mention to you, maybe I did the last two chapters, but we did use OpenCV slightly. We used OpenCV to basically draw or put the text on the images itself. So when I said prediction was this, or put a number on the MNIST image, basically that was done using OpenCV. So let's actually use OpenCV for something a little more cool, which is giving you a live sketch through your webcam. Okay, so now let's bring up this program, this IPython notebook called Live Sketching. And it comes up here. So now you don't actually need this code here. I just left it in to actually so you can test your imports. It's not really necessary. And this is the OpenCV code here that actually will bring up our live sketch. Now, firstly, I'm going to run this for the first time, and I'm going to show you why it's not going to work. There we go. And the error it says here, basically, the C++ code is reporting that it was supposed to get something, but it was empty in this function. And basically, as you can see from the traceback on Python here, this function, CVT color, it basically didn't get an image because it was empty. Alright? And the reason for that is because in Ubuntu, in the virtual machine, we actually have to initialize the webcam first. Now that's basically a one-click process. You just go to Devices right here, and you see something called Webcams here, Integrated Webcam. Basically, by clicking it, it turns it on. And now, if we run this code again, there we go. So this is me here, slouching on my chair. Sorry about that. And this is me here in a sketch, waving and stuff to you. You can actually play with the thresholds if you want after, but it is pretty cool. Kind of does a sketchy outline of me. If I move my laptop around, you kind of see this is my bathroom right here. This is my bedroom in the back. Alright, let's close this here. And as I said, you can actually play with the OpenCV functions. So the OpenCV function that does the edges here is this one here called canny edges. So I forgot exactly what this 10 and 70 do, but if I do remember correctly, it was manipulating basically the threshold sensitivity. So let's try it. This is basically a range from 5 to 70. So let's try from 10 to 70. Let's try 5 to 110. And I'm pretty sure you're going to get more lines in our sketch. Let's find out. No, actually we got less lines in our sketch, so they did the opposite. So now let's undo that. Put back 1070, and let's try to get to 50. And let's put this at 20. See what happens there. There we go. A lot more lines in our text, in our image here. You can see the actual lines in my hand. This is actually pretty cool. So that was our OpenCV demo here. There's a lot of different OpenCV functions going on here. There's Gaussian blue, changing the image from gray to color. Color to gray, sorry. Some thresholding. If you really do want to learn what's going on here, which is not necessary for the deep learning part of this course, please feel free to do my OpenCV course. It's included free in this course, 3 hours of it are free. So go ahead and enjoy if you want to learn it. If not, let's get started with learning about neural nets. Okay, so now